Okay, so today I want to talk about Lie series and how they are used for killing, for getting rid of some of the terms when one does normal forms. Okay, so we have a Hamiltonian. Okay, then we have we have a symplectic form represented by this matrix, and then so its flow, right? So if this we call this Q, we call Z prime, its flow. Okay, is given by this OD, that's a Hamiltonian flow, and also another ingredient for that Hamiltonian flow and another ingredient that I will use is that given two functions, okay, would be a Hamiltonian, that's Hamiltonian, given two functions, okay, we'll define its Poisson bracket at the gradient of F transpose omega minus 1 the gradient of G. Okay? A typical Hamiltonian that one is interested in studying is of the form omega times P plus a half P plus something small, okay, well this is small. This Hamiltonian is very beautiful in the sense of if this small were equals to 0, then we can fully determine the orbits of that Hamiltonian. Okay, so because sometimes we call it, I mean, this Hamiltonian is called integral. Okay, and then there is an object, very beautiful object. Okay, I will leave in the description some bibliography so you can have a look at it, and that is used for doing a change of coordinates of the Hamiltonian, canonical change of coordinates we want to do. Change of coordinates. Okay, we want to do a canonical change of coordinates that makes the Hamiltonian easier. What is a canonical change of coordinates? So the thing is that from this Hamiltonian, from this function, we have an ODE, okay? And we are always interested in studying the orbits of this ODE, okay? But the beautiful thing of this ODE is that this ODE is constructed from this function, okay? Then we want to do a change of coordinates in this ODE such that, okay, we get a new ODE, but in fact this ODE is in fact, again, constructed as another function, okay, giving another function, another Hamiltonian, then you perform again this operation. Okay, that's why we call it, that's what we call a canonical change of coordinates. Okay, canonical change of coordinates satisfy that they are symplectic. Okay, so this is equivalent to be a symplectic change of coordinates. Okay, a symplectic change of coordinates, is from the face to itself, that it satisfies that d f z d omega d f z is again omega. Okay, so the form is preserved, the symplectic form is preserved under the action of. Okay, so if a change of coordinates satisfies this, then there is a new image. Okay, so the idea is the following. So imagine that I have my Hamiltonian. Imagine that I have another Hamiltonian above that. So we have two Hamiltonians. Okay, this one is auxiliary. Okay, we will use this Hamiltonian in order to transform this one. And then this Hamiltonian, okay, F of Z, because it has its own OD, this Hamiltonian has its time t flow. Okay? So time t flow means that the time derivative of this map is equal to this one. Phi, it's easy to see, it is simplex. Okay, it's a canonical change of coordinates. Okay, and then what we do is that the new Hamiltonian that we will get, the change of coordinates that we do, is this one. Okay, so we fix a time t. This is fixed, this is fixed. Okay, and then we do this change of coordinates. Okay, so we transform the Hamiltonian into another Hamiltonian. Okay, we transform the OD into an OD, into another OD. These two ODs are conjugated, so they have the same dynamic. Okay, but instead of going into the OD, okay, the beautiful part here is that instead of going into the OD, the change of coordinates is performed, okay, at the level of the Hamiltonian, which is very nice. And then this is what it comes here. Is that least series, because in fact, okay, so we have our Hamiltonian and the auxiliary Hamiltonian, and then this new Hamiltonian can be expressed in terms of Lie derivative. Okay? Let's see how do they look like. Okay? So fix Z. Okay, fix Z, and then consider the following function G of t, that is h of phi of t of z. Notice that, okay, and then what we'll do is we Taylor expand. Okay, what we'll do is Taylor expand this function. So for Taylor expanding it, we need at 0, okay? So we need to compute g at 0, the derivative at 0, second derivative at 0, and so on. G at 0 is h at phi at 0 of z. But phi at 0 of z, so the 0 time flow of any vector field is the identity. So g at 0 is h of 0. Good. Let's compute the derivative. So g prime at time t is the derivative of this, that is g h at phi c of z times phi prime at z. So we use the chain rule. But phi prime, so the derivative, the time derivative of phi, okay, the derivative of phi, time derivative of phi, satisfies this one. So this is h by t omega minus 1 gradient of f at phi of t. And we use that this, okay, the differential, what we use is that this is equal to the gradient transpose. So notice that what we get is that the time derivative of t at time t is nothing more than the Poisson bracket evaluated at phi t of z. So we get that the derivative at 0 is the Poisson bracket at z. Okay, so now we see a pattern, okay? Because then we need to compute now the second derivative, okay? But notice that what you have is that if we have a function that is a function evaluated at phi of t, then its derivative is the Poisson bracket of this function against f evaluated at phi of t. So what we get, okay, and notice that the key point in the beauty of this expansion, then what we get is that the second time derivative of this is the Poisson bracket of what was it outside against f evaluated at phi of t. So the second derivative at 0 is the Poisson bracket of h, of the Poisson bracket of the Poisson bracket of h f against f at z. So it's not difficult to see that the nth derivative at 0 is nesting all these Poisson brackets n times and evaluating them at z. Okay? So finally, what we get, okay, if we call this, we can call it Li L of H F N. Okay? If we call this recursion of Poisson brackets and times, then what we have is that the Taylor expansion G of t, that is the sum from k equals to 0 plus infinity of the k derivative at 0 n factorial t to the n, okay? At least formally, we are not proving that this converges, although we can prove it, it's not difficult, is L of H against F n at z, okay? Maybe we should put a z here, n factorial t to the n. Okay, so on the fifth, we can write the first term. So we have h of z plus h f of z plus h f of z to factorial plus and so on. Okay, so we have transformed this composition where phi, okay, so where the flow of f is usually unknown, okay, given an any function f, okay, its Hamiltonian flow is unknown. I mean, it's uncomputable, okay, so you cannot get an expression, a closed expression, an analytic expression. But we have transformed this into a formal series, okay. So And these formal series, all its coefficients are, okay, we are forgetting the t squared, and so this formal series is computable term by term. Okay, in principle, given h and f, you have h of z, then you can compute these partial derivatives, then you can compute these partial derivatives, and so on and so on. Okay, so how do we use this to massage Hamiltonians? Okay. So we do it like this. Okay, suppose that as before, we have this Hamiltonian, and then we have this term, and this term is small. Okay? If it were 0, then we will be very happy because we can describe the orbit of this Hamiltonian. If it's non-zero, then, well, I mean, if it's small, then it says that, well, I mean, at least for short times, these orbits are shadowed. Okay, they are perturbed a little bit. But can I do a change of coordinates such that I write this Hamiltonian, okay, as this form plus something that is smaller? And then for doing this, we use that omega is the open time. Okay, which means that for all k in Zn omega times k, okay, for all k in Zn minus 0, there exists gamma and tau such that the absolute value of omega times k is less than this, okay, where k1 is the sum of the components. Okay, so we will use this, and then what we will use is that we will look for, okay, so our goal, find f such that the new Hamiltonian is of the form where this is smaller. Okay, that's our goal. That's our goal. Okay, our goal is that we transform this Hamiltonian into this Hamiltonian where this is smaller. So, how do we do this? Okay, we do it as follows. So, we'll fix t equals to 1 here. Okay, and then we will do, okay, first we will write some of these terms here. Okay, and then see that in fact all these and so on do not play a big role, and these are the ones that play a role. And then we will observe that what's going on. Okay, so how we can heal, or how we can diminish this shear. So for doing this computation, okay, for doing this computation, I will use omega is 0 minus identity 0. So given two functions h and f of z, that is the gradient of h at z Z transpose omega minus 1 gradient of F. Okay, so this is dph, sorry. Partial derivative with respect to of h. Now, what is the inverse of omega? The inverse of omega is 0 I minus I 0. Okay? The inverse of omega, if I multiply omega by this one, I get minus identity. So we get this one. It's quite possible that I'm getting incorrect symbols. I think signs, that's very common. I'm not copying from any notes, so it doesn't matter too much. The important thing is the idea. So what we get here is partial derivative h, partial derivative respect q of h, and now we get minus partial derivative of q f minus partial derivative, sorry, partial derivative of respect f. So what we get is minus partial derivative with respect p of h q of f plus partial derivative with respect q of h partial derivative with respect p of f. Okay? So this is a Poisson bracket. Now, notice. Our goal was to perform this change of coordinates, which is h of z plus Poisson bracket hf of z plus a half of Poisson bracket hf against f and so on. If f is small, okay, if the function f is small, this is small times small. This will be small times small times small. Okay? So we get something that is of size h, small times small, small times small times small. So if the only thing that we want is that we started with a Hamiltonian that was what we desired plus small, and we want to get what we desired plus something that is smaller, I don't care which f I choose, all this will contribute to have something that is at least small times small. Okay? So who plays a role here for determining my f is this part. Okay? I want to choose f such that the expression of h plus Poisson bracket of h f is desired Hamiltonian plus something that is smaller than what we have. Good. So let's see the expression of this one. So we started with h, that was, h was omega times p plus a half p times p plus g, that was small. Okay? So h plus Poisson hf is omega times p plus a half p times p plus g, and then we use what we got from the Poisson. The partial derivative with respect p of h f plus the partial derivative with respect q of h of this one. Okay? Then from this h, we have that the partial derivative with respect p is omega plus p plus the partial derivative with respect p of g. And the partial derivative with respect q of h is the partial derivative with respect q of h, so of g. Okay? So again, we notice the following. No matter, okay, if g is small, the partial derivative is small, and no matter which f we choose, if f is small, we get here small, and this is small. So no, as long as we choose f as big as g, this is small times small, so this part does not contribute. Okay? So the only place where we can play for choosing f is here. Okay? So, what we get is over the desired Hamiltonian, and then plus g minus the partial derivative with respect p of this, that is omega plus p plus dp g times the partial derivative with respect q of f. Okay? Now, again, this is small, this is small. Okay, so this time does not contribute. Okay, does not contribute. So, what we have is over the desired Hamiltonian plus g minus omega plus p times dq of f. dq of f. Notice the following, because we want to do this transformation at p small. Again, this does not contribute. Okay? Because we want to do this transformation that is around this Hamiltonian, but for p equals to 0. So, the only thing to play is over the desired Hamiltonian plus g minus omega times the partial derivative with respect to. So what we want is to kill this term. Kill this term. So now it's a game. Okay, we want to kill g minus dq of f. Okay, so we want this to be 0. Sorry. Omega times dq of f. Okay? We want this to be 0. Now, can this be 0? Okay, let's see. So, g of p q can give less. Okay? In Taylor, in Fourier Taylor coefficients. In this form. And then, if we are looking for an f that is also this form, then this equation, what we want is that because the partial derivative with respect q of this one times omega, okay, is equal to this one, this one I omega times k Q F K B easily R Q. Okay? So if we want to solve this equation, what we want to do is to equate these terms with these terms. Okay, and notice that notice that from here what we get is that at least formally, my F, okay, my F has these coefficients. Okay, so I get F from the capital G coefficients. And now F, we were all the time, so there are several things here to discuss. One is that we were all the time saying, well, F is as small as G. So all these small times small were killed, and so is this true? Well, this is true because we chose that is the often time. We will discuss it in another video. Okay? But if G is small, the coefficients GK are small, and the coefficients of FK are almost as small as these GKs. And this is okay? There is this term, that these terms are called small divisors. Okay? Small divisors, but if one chooses that omega is the often time, this cannot be super bad. This cannot be super small. So if this is small, this is almost likely as small as this one. Okay? This, you don't pay a too high price because of this. And then there is another complaint that I will treat in another video, because this video is getting maybe too long. That is, what happens when k is equal to 0? Can I kill that term? Well, that will be discussed in the next video. And with all this, thank you.